Welcome to Sage Audio. Today, our topic is understanding digital distortion. But first, if you have a mix that you need to have mastered, send it to us to receive a free mastered sample of it with the link in the description. Aliasing or foldback distortion. The distortion types that we're covering here are often related, so we're going to look into those relationships in this video. Also, we'll get into some technical, kind of dry topics, but it's worth watching if you want to better understand this stuff when you're producing or you're mixing. So let's start with aliasing distortion. Now, aliasing is basically harmonics that form in the high frequency range due to our sampling rate being too low to support those high frequencies. So let's say we're using a 44.1 kHz sampling rate, and we have a harmonic that hits 25 kHz. This would in turn bounce back, so to speak. Now, since the highest supported frequency with the sampling rate is 22,500 Hz, or the sampling rate divided by 2, the 25,000 Hz frequency can't be supported. As a result, it folds back in an equal and opposite manner. The sound of these harmonics are often unpleasant, and they can cause phase cancellation to other high frequencies. Although this effect is going to be subtle, let's take a listen to a track with the high frequencies being distorted to cause harmonics to form above the highest supported frequency. Then, we'll turn on oversampling, which is going to lessen the effect of the aliasing. Sample rate distortion. Sample rate distortion is very similar to aliasing. When introducing this type of distortion, we're reducing our sampling rate on purpose, reducing the highest supported frequencies and subsequently causing harmonics in the high frequency range. Although it's not too common of a distortion type, it can be used creatively. Let's take a listen to it. If you're enjoying the video, hit the like button and subscribe if you haven't already. It's free and it helps us bring you more videos. Bit depth reduction distortion. Reducing the bit depth causes multiple forms of distortion, including clipping, quantization noise or error, and wave shaping when the rate is reduced significantly. The bit depth is responsible for approximating the signal's amplitude. The higher the bit depth, the more accurate the approximation or recreation of the waveform. When we reduce the bit depth, we lower the amplitude ceiling, making clipping distortion more likely. Next, we create a bigger difference between the original waveform and the digital or quantized waveform. This results in quantization error, which more or less sounds like noise. Lastly, if we reduce the bit depth enough, the waveform can completely change due to clipping and general unsupported amplitudes the waveform had originally. So let's take a listen to it by using this bit depth reduction plugin, and notice how significant the changes are when lowered to 8 bits and below. Clipping distortion. We touched on this last chapter, but let's take a look at it again. In a digital system, we're usually working with 64-bit processing. This means our signal can go well above 0 dB before clipping occurs. However, by the time it reaches the output, it's converted back to 24-bit processing. Now, this is why meters in a DAW usually don't show red when overs happen on a track or a bus, but it does show red at the output. As for the clipping itself, it's basically the transient being chopped off at the top, however much it goes over 0 dB. As a result, we get white noise whenever the hard clipping occurs. Let's take a listen to hard clipping being introduced, and then listen to the delta or the null of this clipping to hear exactly what is being changed about the signal. Pre-ringing distortion. Pre-ringing is a newer term, but it refers to the effect that linear phase processing has on transients. In short, when we introduce linear phase processing, the signal is delayed by a set amount. Our DAW then tries to compensate for the offset timing. In doing so, the original signal and the delay compensated signal clash very slightly, causing mild but sometimes noticeable phase cancellation to our transients. Although this is going to be subtle, let's take a listen to one track processed with 0 latency and one processed with an aggressive linear phase setting. Lossy file distortion. You might be familiar with the term lossy file. This is basically an MP3 or similar file type in which some information has been deleted to reduce the file size. As you'd imagine, this process causes distortion, which we can emulate with this codec plugin. Now, the main cause of distortion in these files are bitrate reduction. The bitrate is a multiple of our bit depth and sampling rate. For example, 16 bits multiplied by 44,100 samples times 2 to make the signal stereo results in 1,411,200 bits per second, or roughly 1,411 kilobits per second. Now, MP3s range from about 128 to 320 kilobits per second. So in short, to create a lossy file type, we need to reduce the sampling rate and bit depth, causing noise, potential clipping, a reduction to high frequencies, and potential aliasing if filters aren't being used. So let's take a listen to this codec plugin and solely focus on the effects of reducing the kilobits per second. Sample dropout distortion. If a sample or a group of samples drop out or are deleted during the conversion process from lossless to lossy file types, we'll notice an audible drop in the signal, which sounds somewhat like a click. We could emulate this with the codec plugin. Let's take a listen to it and to what these dropouts sound like. If you're enjoying the channel, use the search box to watch more of our videos. Encoding distortion. Encoding error or distortion is another term that you might have heard. In short, it's very similar to lossy distortion, but it typically refers to the clipping aspect. When online streaming services convert WAV files into lossy file types, they reduce the bit depth, causing less accurate amplitude approximations. Now, subsequently, transients that wouldn't have peaked are now hitting a lower ceiling, resulting in hard clipping distortion. To illustrate this, I'll use this plugin by Apple that lets us monitor a WAV file being encoded. Intersample peaking. Intersample peaking occurs when the digital waveform is converted back into an analog waveform by a D to A converter, which occurs in any amplifier that converts digital audio into analog for speakers, earbuds, etc. Now, during this conversion, peaks at 0 dB or close to it can be read incorrectly. Now, this results in those peaks being amplified above 0 dB, resulting in clipping distortion. Now, fortunately, the better D to A converter that you have, the less of a problem these are. Let's try to emulate them though with a hard clipper, and notice that the effect is subtle and honestly doesn't have the worst sound. True peak distortion. You might have noticed that some limiters have true peak detection and limiting functions. Now, these were designed to reduce intersample peaking. Ironically, they introduce a separate form of distortion, similar to the linear phase distortion that we covered in Chapter 5, in which transients are affected via phase cancellation. Now, with that in mind, if you see a limiter with true peak limiting, not detection but limiting, it's best to disable it for the sake of preserving transients. Let's take a listen to a mix limited with true peak limiting and one without, and let me know if you could hear a difference. If you have a mix that you need to have mastered, send it to us to receive a free mastered sample of it with the link in the description. Thank you so much for watching.